Hello guys, we want to start our 10th lecture. So in this lecture, we want to see application of Laplace transform in solving second order initial value problem. And after that, we want to see behavior of Laplace transform of a function when s approaches infinity. So for solving second order initial value problem, we start with one example. We want to find yt in following second order initial value problem. We have y double prime minus 10y prime plus 9 times y is equal to 5t. So again, here all the coefficients are constant. So we have y at t equal to 0 is minus 1 and y prime at t equal to 0 is plus 2. In order to solve this problem, we have to have the same procedure that we had for first order initial value problem. So we have to take you have to take Laplace transform from both right and left side of the equation. So if from the left hand side of the equation, we have Laplace transform of y double prime minus 10 times Laplace transform of y prime plus 9 Laplace transform of y, it's equal to 5 times Laplace transform of t as a result. So Laplace transform of y double prime based on transform of derivatives, so we have is equal to s squared times y capital S. What's y capital S? Y capital S is equal to Laplace transform of yt. So it's s squared times y capital S minus s times y at t equal to 0. So this y is small y, is a function of t, it's not y capital, which is Laplace transform, minus y prime at t equal to 0. So it's Laplace transform of y double prime minus 10 times Laplace transform of y prime is s ys minus y at t equal to 0 plus 9y capital S is equal to 5. Laplace transform of t is 1 over s squared. So now I factor out y capital S. So what we have here, we have s squared times ys minus 10 s ys plus 9 here ys minus what's y at t equal to 0. Y at t equal to 0 is minus 1. Minus 1 times minus s is plus s minus y prime at t equal to 0, it's 2 minus 10 times minus y at t equal to 0, it's minus 1 times minus is plus, plus times minus is minus 10. It's equal to 5 over s squared. As a result, ys times s squared minus 10s plus 9, it's equal to 5 over s squared minus so here we have 12, so s minus 12. So it means that ys is equal to 5 over s squared minus s minus 12 divided by s squared minus 10s plus 9. If I want to simplify ys more, so we can say ys is equal to here we have s squared, so 5 minus s squared times s minus 12 divided by s squared minus 10s plus 9. Now I factor denominator, so we have s squared minus 10s plus 9. If I factor denominator, we have s minus 1 times s minus 9. And in numerator, if I simplify it, I have minus s cubed plus 12s squared plus 5. And we have 1s squared, so I can put it in denominator. So now I have to find partial fraction in terms of these functions. So if you look at the table of partial fraction, you can see that if we have this function minus s cubed plus 12s squared plus 5 divided by s squared times s minus 1 times s minus 9, the partial fraction terms are a divided by s plus b divided by s squared plus c divided by s minus 1 plus d over s minus 9. So now we have to find a, b, c, and d. In order to find a, b, c, and d, so I just add these four partial fraction terms. So we have here s squared times s minus 1 times s minus 9. So in numerator we have a times s minus 1 times s minus 9 plus b times s minus 1 times s minus 9 plus c times s squared times s minus 9 plus d times s squared s minus 1. Now I use the second approach, so I assume that s is equal to 0. If s is equal to 0, right hand side of equation we have minus s cubed, so it's minus 0 plus 12 times 0 plus 5. So in left hand side of equation we have 5, and in right hand side of equation 0 times a is gone. 0 minus 1 is minus 1 times minus 9, so it's 9 times b. C times 0, 0, d times 0, 0. As a result, b is equal to 9 over 5. It's 5 over 9. Is 5 over 9. So now I plug s equal to 1. As a result, in left side of equation, minus 1 cubed is minus 1 plus 12 is 11 plus 5 is 16. In right hand side of equation, so we have 1 minus 1 is 0, a times 0 gone, b times 0 is gone. So c times 1 times minus 8, so it's minus 8c. And d times 1 minus 1, so it's 0. So 0, as a result, we can say c is equal to minus 2. Now I plug s equal to 9. So left side of equation minus 9 to the power of 3 plus 12 9 squared plus 5. So it's going to be 248. Right hand side of equation, so we have 9 minus 9 is 0. We have b times 9 minus 9 is 0. We have c times 9 minus 9 is 0. So we have d. 9 minus 1 is 8. 8 times 9 squared is equal to 648 times d. As a result, d is equal to 248 divided by 648. If you simplify, you can see it's equal to 31 divided by 81. So now we have to find a. In order to find a, so you can plug any random number to find a, because you already know b, c, and d. If you plug any random number, so you can easily find a. So I assume that s is equal to 2. So left side of equation, minus 2 cubed plus 12 times 2 squared plus 5 is going to be 45. Right hand side of equation, we have a times 2 times 1 times minus 7. So it's minus 7. 2 times minus 1 is minus 2. Is plus 2 times minus 7 is minus 14. Minus 14a. So for b, we have 2 minus 1 is 1. 2 minus 7 minus 7. Minus 7 times 1 is minus 7. So it's minus 7 times b. For c, we have 2 squared is 4. 4 times 2 minus 9 is minus 7. So minus 28 times c. Plus s, so is 2. 2 times 2 squared is 4. 4 times 1 is 4. So plus 4d. We already know b, c, and d. As a result, we can easily find a. A is equal to 51. 50 over 81. So we could find a, b, c, and d. As a result, ys it's equal to a, which is 50 over 81 divided by s, plus b, which is 5 over 9 divided by s squared, minus c is 2 over s minus 1 plus 31 over 81 over s minus 9. So now we can easily find yt. Yt is Laplace inverse of ys. So 50 over 81 over s, Laplace inverse is 50 over 81. 5 over 9 over s squared. So it's Laplace transform of 5 over 9 times t. Minus 2 over s minus 1. So it's 2e to the power of t plus 31 over 81 e to the power of 9. So we could find yt. In this section, you want to see behavior of Laplace transform when s approaches infinity. So we already found some Laplace transform of some functions. For example, 1 is 1 over s, t to the power of n is n factorial over s to the power of n plus 1, and so on. For all these Laplace transforms, so we can see that when s approaches infinity, fs approaches 0. But we want to see if it's valid for all the functions or not. First of all, we can say that if ft is a piecewise continuous function on the range of 0 to infinity and its exponential order, then limit of Laplace transform of ft or fs when s approaches infinity is equal to 0. But so it's just for piecewise continuous and exponential orders for functions. For example, in future we can see we will see one function which is called unit impulse function. So unit impulse function, and so we will see we define it as 1 over epsilon when t is between 0 and epsilon, and it's equal to 0 for t greater than or equal to epsilon. So this function is not piecewise continuous function, but in future we can, if I just call this function, let's say f is equal to this function, unit impulse function. So in future we will see that Laplace inverse of, so Laplace transform of f is equal to 1. In fact, this function is not piecewise continuous, but it has Laplace transform. Its Laplace transform is 1, but what's limit of Laplace transform of ft when s approaches infinity? So here we have a function, it's a constant function, as a result is equal to 1. So we can see that limit of Laplace function in this case is not equal to 0 when s approaches infinity. Why? Because unit impulse function is not piecewise continuous function. So behavior of fs when s approaches infinity is equal to 0 just for piecewise continuous function and exponential order functions. In the next part, I have a question from. So is Laplace transform of a function unique or not? So we will see here that Laplace transform of function is not unique. For example, if we have Laplace transform of f1, it's equal to Laplace transform of f2, we cannot say, okay, so f1 should be equal to f2. No, we cannot say that. Now I give you one example that two functions are not equal, but they have the same Laplace transform. For example, let's assume we have a function f1, it's like this, e to the power of 3t for all the t's, but t cannot be equal to 5, but when t is equal to 5, so we have 1. The other function is equal to, it's not with two equations, the other function is just e to the power of 3t. If two functions want to be equal, they have to be equal for all the magnitudes of s. But here, if for all the magnitudes of t. For example, here, f1 at 5, it's 1, but here f2 at 5, it's equal to e to the power of 15. So you can see that 1 is not equal to e to the power of 15. As a result, f1 is not equal to f2. These two functions are not equal, but Laplace transform of f1, so you can find it by definition, it's 1 over s minus 3. Laplace transform of f2 is equal to 1 over s minus 3. So now you can see that we have Laplace transform of f1 and f2, they are equal, but f1 is not equal to f2. So Laplace transform of f1 is equal to Laplace transform of f2, but so it's not conclusion, but f1 is not equal to f2. Just under one condition, we can say if Laplace transform of f1 is equal to Laplace transform of f2, then f1 is equal to f2. So we can say if f1 and f2 are continuous, on the range of 0 to infinity, and Laplace transform of f1 is equal to Laplace transform of f2, then we can say that f1 is equal to f2. So under this condition, if Laplace transform of f1 is equal to Laplace transform of f2, we can say f1 is equal to f2. But you know, for our example here, so f1 was not continuous on the range of 0 to infinity.